Let's take a look at energy flow through ecosystems. And this should be pretty brief. We've really talked about energy flow for a long time now, so I don't think you're really going to have much trouble with it. We all know, we've gone over before, for most of the planet, sunlight serves as the major input of energy. It's really the only thing we have coming from outside the planet, outside our biosphere. There has to be a continuous source of energy, and that source of energy for most organisms on the planet is sunlight. That sunlight is harnessed in photosynthesis and converted to glucose, and that glucose is converted to ATP, and that ATP runs metabolism. And that's true for every single organism on the planet. They can't all use all the energy stored in glucose. If you don't have mitochondria, if you live in places that don't have oxygen, but you still get some ATP from the glucose, and you still use that ATP to do your metabolism, all the chemical reactions that need to go on in whether you're talking about a cell or an organism. So when we look at it that way, we end up with kind of pyramid structure. So at the base of that pyramid, we have producers. And producers are able to take sunlight and turn it into glucose. They use that glucose to make ATP so that those producers can do their metabolism. And we said, because of the second law of thermodynamics, when you convert energy from one form to another, or from one system to another, you are going to lose most of it. In fact, you lose, we said yesterday, 90% of the energy is lost. Only about 10% gets to what you want it to do. So 90% of sunlight is lost, 10% goes to feed, basically to feed producers. And those producers are then able to support a certain number of herbivores. But 90% of the energy available in producers, only 10% of that makes its way to herbivores. But that is a reason that herbivores can be large. If you think of large animals, you probably think of elephants. Let's see, blue whale, giraffe. Even if we go back to dinosaurs, the Brontosaurus, these very large organisms are all herbivores. Now, the blue whale doesn't eat plants, but it eats phytoplankton, which are the producers in the ocean. So, large organisms tend to be herbivores. These herbivores can support or provide enough energy, so 90% of the energy is going to stay there, 10% will go up. These would be secondary consumers. And those secondary consumers can support a certain amount of carnivores. So these are probably omnivores and carnivores. And you can see that each time you go up in a chain or in the pyramid, you leave 90% of it in the layer below. So 90% of the energy that producers have is in the producers. Only 10% of that moves up, and only 10% of that moves to other consumers. And this is the reason that food chains have a limited length. So this is our pyramid way of looking at it. If we looked at a food chain, we would start with a producer. Not a very good plant, but let's use our imagination and pretend it's a plant. That plant might be eaten by a mouse. Let's see if we can draw a mouse. And that mouse can be eaten by a fox. And that fox could be eaten by a human, but probably that fox is at the top of this food chain. And it would be difficult to describe a food chain that is more than 6 organisms. Because 90% of the energy in that producer is going to remain in the producer. 10% of it will make it to the mouse. That means that this fox has to eat a lot of mice to keep its amount of energy. So these mice eat a lot of plants. Fox eats a lot of different mice. There aren't many things that could get to the fox. But if you go from producer to an apex predator, you're limited to, in most cases, 4 or 5 organisms. If you really stretch your imagination, you might get it up to 6. And that has to do with the loss of energy at each level. Now, food chains are nice, simple ways to look at it. Mice eat plants, fox eat mice, but we know actually that cats eat mice, owls. So really, there are multiple predators for the herbivore. There are multiple predators for these organisms. Plants that mice eat are also eaten by other organisms. So this type of plant doesn't support just mice. It would also support things like crickets, rabbits, all kinds of organisms that are going to feed on plant life in an area. So a better representation, at least a more detailed representation, is to use a food web to describe relationships. But they're all following energy relationships. And most of them begin with the sun. They go to producers. They go to primary consumers, secondary consumers, and in the end, although it looks like we're following matter, the mouse obviously is matter, the fox is matter, the plant is matter. In this case, our discussions are really focused on the energy movement. And the energy movement, no matter what organism it is going to be sunlight to glucose to ATP. So this is light, chemical, and chemical. And then finally that ATP is used for, in most cases, mechanical, moving something in a cell. All right, I will put up the assignments for section 2, and keep up the good work. I know you're all working very hard. We are getting close to the end of the year, and I appreciate everyone who is working on this material.